All right, I'm going to work the exact same problem from the last video, just now again, specifically adding in friction here. So I'm going to have a coefficient of friction of 0.12 as we slide our 13 kilogram box up our 1.2 meter long ramp with a height of 0.94. In the last video, we had already solved for the angle, right? You were only given two things, and we solved for the third. It was about 58 degrees, so I went ahead and inserted that in here so we didn't have to go back through that. Now, total work is going to equal work you have to use lifting the object plus the work done by friction. Now let me explain why that is. Work is a scalar, not a vector. What that means is you don't have to break work down into its components because it has a direction. Work does not have a direction. It's just the amount of energy that's expended when displacing an object. It's how much energy you spend doing something there. It's just a number. So you can simply take works and add them together, neglecting what direction it was done in. That doesn't matter, the direction of work, okay? So if you're thinking about how much work you are expending, in the last video we showed that you use the exact same amount of work lifting an object up as you do sliding it up a ramp, neglecting friction. So we can just use work lifting for how much work you have to do because of the ramp, right? How much work does it take to lift it straight up there? But there's another thing in this one. Work you have to do to overcome friction. You have to beat out friction, right? And because of that, you're going to do a little bit extra work. Another way to think about this is how much energy is friction going to steal, aka how much extra energy do you need to put in? All right, so let's go ahead and start working this down. Total work is going to equal force of lift times delta y, specifically how high you have to lift it up, plus force of friction times delta, and I'll call it delta x being the length of the ramp there. So how much work you have to put in to overcome friction, force of friction times how far friction gets to act. All right, well, I don't know force of lift here, but that's relatively easy to find out. We did that in the last video, right? If you're going straight up and down at a constant velocity, then you're going to have force of lift is going to equal your force of gravity, right? That was done in the last video. We set up a free body diagram to help us with that. So force of lift, in this case, going at a constant velocity, is going to equal mg. So I know this now. Force that's required to lift straight up at constant velocity, mg delta y, plus I have an equation for force of friction. It breaks down to mu normal force delta x now. All right, so all I did here was I substituted in force of lift, mg, from what we learned in our last video, and I broke force of friction apart into mu times normal force. The delta y, the delta x, that all remained exactly the same. Now let's kind of go through this. I know the mass, I know gravity, I know delta y, 0.94. I know mu, 0.12. I don't know the normal force. I do know delta x, 1.2. So I need to come over here and try to find normal force. To do that, free body diagram of the object tilted on the axis, right? Because I'm actually looking here at sliding it up the ramp. That's where friction is acting, along the length of the ramp, tilted. So that's my tilted free body diagram. Notice Fg sine theta is gravity going down the ramp. Fg cosine is gravity going into the ramp. And here, to get normal force, all I need is the y-axis. So I'm going to go ahead and set that up for us. Y-axis, sum of the forces equals ma. If I call up positive and down negative, that's going to leave me with normal force minus Fg cosine theta equals, and I can assume acceleration is 0. The object isn't flying up into outer space, plunging down into the depths of the earth. Meaning normal force, I'm going to go ahead and break Fg down into mg here. Fg is equal, or normal force is equal to mg cosine theta there. All right, so now that I know this, I can substitute him in, and I'll know everything that I could possibly need here. Total work is going to equal to mg delta y. That's the work needed as if we were lifting it straight up, plus the work that friction stills, mu mg cosine theta times delta x. And now I plug in numbers and punch it in my calculator. Whenever I plug everything into my calculator, sorry that I was kind of running out of space and I kind of ran all the way over here for my mu, m, g, cosine theta, delta x part from the work done by friction. I come out with total work is 130 joules. So this was the part that without friction, just the lifting part, what we did in the last video, it came out to be around 120 joules with significant figures. And with sig figs, friction over here adds about 10 extra joules of work. You got to do an extra 10 joules of work if friction's there, in this case with a coefficient of friction of 0.12.